Hi, in this session we will be discussing about how to solve linear non-homogeneous recurrence relations with constant coefficients. In the previous session we have discussed about homogeneous recurrence relation. Okay, I hope you know what is a recurrence relation and what do you mean by a homogeneous recurrence relation. So generally the linear recurrence relation will be of the form some C naught an plus C1 an minus 1 plus etc plus Cn v naught. So when the right hand side is 0, this will be homogeneous recurrence relation, and also if these C constant C1 etc, if they are if these coefficients C0 C1 C2 etc Cn are constants, we'll call it constant coefficients. So if the right hand side is a function, it will be called function, for example a function like 2 raised to n, or maybe like sine n, sine something, sine n 2n, like that. So if the right hand side is a function, or specifically if it is of the form some f of n, okay, it will be called a non-homogeneous recurrence relation. Okay, so here we will be discussing the solution of linear non-homogeneous recurrence relations with constant coefficients. So I hope you understand what do you mean by recurrence relation. It contains terms of the previous terms of the sequence, and I hope you know the linear, the equation is linear. What do you mean by the linearity of the equation? All the terms will be have power 1 and none of the terms would be multiplied. All the terms will have power 1 and none of the terms will be multiplied together. So I hope you understand what do you mean by linear, and also what do you mean by non-homogeneous. If it is homogeneous, your right hand side would be 0, the term which is independent of all any terms of the sequence, okay, that will be 0, and if the right hand side is non-zero, it will be called a non-homogeneous recurrence relation. Okay, so I hope you understand these terms. Okay, let us recap. In the so basically we will be considering only second degree equations. This theory can be carried over to any degree also. So when you recap, so we had studied that when first the solution of homogeneous recurrence relation, what you do is we will write the characteristic equation first. Okay, we will write the characteristic equation first by putting just an is equal to c into r raised to n. Then you will get a equation terms of r. Okay, so if you solve for r, suppose you get distinct real roots, for example you get r1 comma r2, then your solution would be c1 r1 raised to n plus some c2 r2 raised to n, where the c1 and c2 are obtained from the initial conditions. Now if this r1 and r2 are same, for example if r1 is equal to r2, we will supply a n to prevent them from combining. Okay, first it is c2 c r1 raised to n. So if both roots are same, we will supply an n to prevent them from combining. If you have three roots which are same, you will again make an n square there, c2 r1 raised c3 r1 raised to n. Okay, so this is how you write for equal roots. Now for complex roots, the thing was, if you get the roots as plus or minus a plus or minus bi, you will first you find r, which is equal to root of a square plus b square, and also you find theta. Then your solution will be simply r raised to n, then cos n theta cos n theta plus sine n theta. So this will be your solution. Okay, so this was the solution pattern for homogeneous recurrence relation. For details you can refer the previous video. Now we will be discussing non-homogeneous recurrence relation. In that also the solution, just like differential equation which you have studied in the linear differential equations, in the case of non-homogeneous linear differential equation, the solution had two parts. First was the general solution, plus you had the particular solution. So the solution in the case of linear differential equation was of this form. The first one was the solution of the homogeneous part, and the second one was a particular solution. So similarly in this way also, the solution of non-homogeneous recurrence relation, it will have two parts. So the first part would be an h. This will be the solution of the homogeneous corresponding homogeneous recurrence relation, plus you will have an p, which will be solution of the corresponding particular, which will be particular solution to the given problem. Okay, so the total solution will have two parts. One is the solution of the homogeneous part, and then a particular solution. So you will have to do it in two steps. First you have to write the corresponding homogeneous equation, you have to find the roots, and then you have to write the format, then you have to find the particular solution. Now there is no fixed method to find the particular solutions, it's very difficult. So what you do is that you use undetermined coefficients method, where you are using some notions, you are using some estimates to you are using some estimates to the particular solution from previous experience. So there are some you have to study some standard forms only. There is no particular formula for a general function. You can only have some idea from experience. So what you do is that you will have a table which will tell you the standard solutions to some standard type of problems. Okay, so sometimes your right hand side would be simply some constant, so it will have a standard solution would be there. Sometimes your right hand side will be some r raised to n, or sometimes it may be some power of n, and maybe it's n square plus 2n plus 1. So all this will have a standard solution is there, so you'll have to memorize that standard solution, and we'll use those ideas to solve the problem. So we'll see those forms now. Okay, so I hope you understand that the solution has two parts. One is the homogeneous part, and the second one is the particular solution. The homogeneous part we all know from previous session how to solve it, and we'll now discuss methods to find this particular solution part. Okay, so before that, try to jot down this table. Okay, so this is the table here. So if your right hand side is a constant, our estimated solution for A and P would be simply, we will assume that some constant is the solution. Okay, the particular solution. We'll do the problems related to that. Suppose your right hand side is n, we'll write in first order polynomial, which is simply some a1n plus a0, and then we'll determine a1 and a0 for the particular problem. Okay, so your solution, if it is n, would be simply a1n plus a0. So you'll have to write a polynomial of degree 1. So this is the general formula for a polynomial of degree 1. Similarly, if your right hand side is n square, we'll write a general formula for a polynomial of degree 2, which is nothing but a2n square plus a1n plus a0. So similarly, I hope you know how to write n cube. If it is n cube, just for write what is it, a3n square n cube plus a2n square plus a1n plus a0. So this is the general form. Even if your right hand side is a polynomial like this, n square plus n plus 1, then also your solution will be a general polynomial of degree 2. So it will be similarly a2n square plus a1n plus a0. So these two terms will cover all possible cases in which your right hand side is a polynomial. And now if your right hand side is just r raised to n, your assumption of solution will be some constant into r raised to n will be the solution. So we will do some problems related to that, and then we'll come to the rest of the terms. And also there are also terms involving sine and theta, cos and theta. Okay, for them also there are methods are there. So first we'll do some problems, and then we'll come down to these things. Okay, so for sine and theta, it is, we are assuming the solution to be a sine and theta plus b cos and theta. And for cos and theta, the solution is assumed to be a sine and theta and b cos and theta. These tables are available in the standard textbook. And similarly, if it is a polynomial into r raised to n, it will be r raised to n into that general polynomial in ith term. Similarly, for r raised to n sine theta and theta also, this is the standard form. So in order to find the particular solution, there is no fixed method. Only way is we'll have to memorize this table, and if your right hand side is any of these functions, you have to write the corresponding form. We'll substitute this corresponding form into the equation, and then we'll find the values for this a1 and a0 and a2, etc. That is how we'll be doing the problems. So to elaborate further, let us try to do one problem now. So suppose your problem is like this. Your problem is an plus 2 plus 3an plus 1 plus 2an is equal to 3 raised to n. So we'll have to find a solution. So as discussed earlier, this is a linear non-homogeneous equation with constant coefficients. So the solution will be of the form an h plus an p. So I hope you understand this step. And now to find an h, we will write the corresponding homogeneous equation, which is nothing but an plus 2 plus 3an plus 1 plus 2an is equal to 0. The solution of this will be lying in the characteristic equation, which is nothing but r square plus 3r plus 2 is equal to 0. My solution of this is nothing but r is equal to minus 2 and minus 1. Hence the solution of the corresponding homogeneous equation would be simply some constant, so an would be simply, anh would be simply some c1 into minus 2 raised to n plus some c2 into minus 1 raised to n. So this is the solution of the corresponding homogeneous equation. Okay, now we will try to find the corresponding particular solution. So we'll try to find solution of a and p. Now your right hand side is of the form 3 raised to n, which is of the form r raised to n. So your solution is assumed to be of the form some constant into r raised to n. So I'll assume the solution as a r raised to n. Now we will try to find the value of this a. Okay, now if you substitute this value of an in this equation, your equation will be, your an plus 2 would be simply a r raised to n plus 2, and your an plus 1 would be simply a r raised to n plus 1. So you substitute this, so you will get this as a into r raised to n plus 2. So your r is here 3, so a into 3 raised to n plus 2 plus 3 into a into 3 raised to n plus 1 plus 2 into 3 raised to n is equal to 3 raised to n. So this is obtained by directly substituting the values in the given equation. So now from this equation we'll try to find the value of a. So it is actually so 3 raised to n you can cancel to everywhere. So it will be 9a plus 9. So sorry, if you can 9a plus, again you have 9a and then 2 into 3 raised to n, so you will be plus 1 is equal to 0. So this is 2 into 3 raised to n here. So when you solve this, you can cancel out 3 raised to, you can take 3 raised to 8 and cancel out uniformly. So you will get it as 9a. So because 3 raised to n will be going from this term, so it will be 3 raised to n will be going, only 3 square will be remaining. So 9a you will get in the first term. Similarly in the second term you will get 9a, and the third term 2 into 3 raised to n minus 3 raised to n will be actually 3 raised to n. So your equation is like this: a into 3 raised to n plus 2 plus a into 3 raised to n plus 2 plus 3 raised to n is equal to 0. So when you cancel out this 3 raised to n, what will happen? We'll get this as 9a plus 9a plus 1 is equal to 0. Therefore that means 18a is equal to 1 is equal to minus 1, or a is equal to minus 1 by 18. So your solution would be simply be equal to it will of the form a and p is equal to minus 1 by 18 into 3 raised to n. So your final solution would be an is equal to c1 minus 2 raised to n plus c2 minus 1 raised to n plus minus 1 by 18 into 3 raised to n. So in order to find c1 and c2, you can use the initial condition which says that an is equal to it is not an equal to 0, it is actually a0 is equal to 0 and a1 is equal to 1. You can substitute here. So when n is equal to 0, you will have c1 plus c2 minus 1 by 18 is equal to 0, and when n is equal to 1, you will have 1 is equal to minus 2 c1, then minus c2, then minus 1 by 18 into 3. From this you can find the value of c1 and c2 and you can substitute it. You can try it yourself. So I hope you understand this problem. Okay, we will do one more problem now. Okay, so in some cases there will be slight complication here. So suppose you are considering this problem here. So this is also a homogeneous equation with constant coefficients. So first of all, it will have two parts, which is nothing but an into h plus an into p. Now to find an into h, we will consider the equation an plus 1 minus 2an is equal to 0. The solution of this will be contained in the characteristic equation, which is r minus 2 is equal to 0. Therefore r is equal to 2. Therefore your a n h would be nothing but c1 into 2 raised to n. So this is the homogeneous solution. Now to find the particular solution, so it is of the form 2 raised to n. So your solution would be of the form a and p would be of the form some constant into 2 raised to n. So okay, so you will have the solution will be like c1, so a1 would be then c1 into 2 raised to n plus a into 2 raised to n. But the problem is that if you write the solution as 2 raised to n, in effect you will have the solution as some constant into 2 raised to n only. Actually there will be no scope for particular solution in this method. Okay, so what you do is that this a problem here occurred because this 2 raised to n has been combined with the homogeneous solution. That was because this 2 raised to n was already present in the homogeneous solution. So we need to prevent them from combining it. So for that to prevent them from combining, I'll write the particular solution as 2 raised to n into n, just like the thing in case of equal roots. So in order to prevent them from combining, I'll assume the solution to be of the form a into n into 2 raised to n. Okay, so now we'll consider the a and p as just a into n into 2 raised to n. So if you add 2 raised to n twice in the homogeneous, suppose your homogeneous solution was like this: c1 into 2 raised to n plus c2n into 2 raised to n. In that case, you will write your particular solution as n square into 2 raised to n, some constant into n square into 2 raised to n, to prevent them from combining with the c1 and c2. Okay, so according to the multiplicity, you will have to write the particular solution. Okay, so now we are assuming the solution was simply a and p as a into n into 2 raised to n. So we will try to find the value of a from this. So when you substitute this a n into the given equation, which is a n plus 1 minus 2an is equal to 2 raised to n. So when you try to find the solution, we will just apply this thing here. So it will be a n plus 1 into a into n plus 1 into 2 raised to n plus 1 minus 2 into a into n into again 2 raised to n, which is equal to 2 raised to n. So you will have the solution. You will try to find the value of a from here. So when I rewrite this, it will be simply be a into n plus 1 into 2 raised to n plus 1 minus a into n into 2 raised to n plus 1 is equal to 2 raised to n. So here a into n into a plus 1 will get cancelled out. So it will simply be a into 2 raised to n plus 1. Okay, when you expand this, a into n into 2 raised to n plus 1 will get cancelled out. So the remaining thing would be a into 2 raised to n plus 1, which is equal to 2 raised to n. So similarly, your a will be 1 by 2 because you can cancel 2 raised to n and 2 raised to n here. So it will be simply be 1 by 2. So your solution is, your particular solution is a and p will be equal to 1 by 2 into n into 2 raised to n. So your final solution would be an would be equal to c1 2 raised to n plus 1 by 2 into n into 2 raised to n. So in order to find c1, they have already told you that a naught is equal to 1. So we'll substitute that here. So when n is equal to 0, you will have a naught is equal to c1 plus c1, which is equal to actually 1. So your solution of c1 is 1. So your final solution would be an is equal to c1 is 1 here. So 2 raised to n plus 1 by 2 into n into 2 raised to n. So this is the solution here. So I hope you understand the problems in which already the homogeneous solution as a factor are like the particular solution. You have to supply an n to prevent them from combining. Okay, we'll do one more problem here. Okay, so your problem here is an plus 2 is equal to, so the solution is like earlier, it will have anh plus anp. So for anh, consider an plus 2 plus 4an plus 1 plus 4an is equal to 0. So the corresponding homogeneous equation will be, characteristic equation will be r square plus r plus 4 is equal to 0. So your r is actually minus 2 repeated roots. So the solution, particular homogeneous solution will be anh is equal to basically c1 into minus 2 raised to n plus c2n, in order to prevent them from combining, minus 2 raised to n. So this is the homogeneous solution. For particular solution, your right side is of the form constant. So we'll assume that the solution is also of the form a constant. So substituting this, so you'll assume that your an is also, anp is a constant. Substituting this in the given equation, we'll have an plus 2 is again constant only, plus 4a plus 4a is equal to 7, because even if it is an plus 2 or an everything, you will get the particular solution as a only. So your an plus 2 will be 4, an plus 1 would be 4. So that in substituting these things, it will be simply 9a is equal to 7, or a is equal to just 7 by 9. So your solution would be plus 7 by 9. Okay, in order to find c1 and c2, they have given you two conditions, which says that a naught is equal to 1, a1 is equal to 2. You have to complete that also. So how will you do it? So you just substitute. So when it is when a naught is equal to 0, your n would be 0. So when you do that, what will you get? Okay, just a second. Okay, so just a second, please wait. So okay, so in order to find, so when you substitute, if when you find a naught, what will happen? You will have the value of an will be 1. Okay, and right side will be c1 plus c2 into 0 plus 7 by 9. So we'll have c1 plus 7 by 9 is equal to 1 equation. Now to find a1, substitute 1 here. So we'll have a1 will be 2. That means c1 into minus 2 plus c2 into minus 2 plus 7 by 9 is equal to 2. So from these two equations, you can try to solve the value of c1 and c2. Please do it. It's basically linear equations, so you can find it. Okay, again we'll do one more question here. So we'll have a solution of this form. Solve the recurrence relation as before. The solution has two parts, anh plus anp, right? So anh, you have to consider r square minus 6r plus 9 is equal to 0. The solution of which is nothing but 3 comma 3, right? So so 3 comma 3. So solution would be of the form anh would be of the form c1 3 raised to n plus c2n 3 raised to n only, and your right side is of the form 3 into 2 raised to n. So the solution, so your particular solution will be of the form a and p would be equal to some a into 2 raised to n plus b into 3 raised to n, but already 3 raised to n is suffering 2 times here, so we'll supply n square to prevent them from combining. So this will be your solution here. I hope you understand how to write solution now. So in order to find the value of a and b, what you do, you just apply this in the given equation. So your an plus 2 would be simply a into 2 raised to n plus 2 plus b into 3 raised to n plus 2 into n plus 2 square minus 6 into an plus 1 is a into 2 raised to n plus 1 plus b into 3 raised to n plus 1 into n plus 1 square, okay, plus 9 into a n is nothing but a into 2 raised to n plus b into 3 raised to n plus n square. Now the value of this is equal to what do you say, it is actually equal to 3 into 2 raised to n plus 7 into 3 raised to n. So we will compare these things here. So what will you get? So when you simplify these things here, so you will have a into 2 raised to n plus 2 is there, and then next n 2 raised to n is coming here, minus 6 into 2 raised to n plus 1 is there, then plus 9 into 2 raised to n is there, okay. Similarly with b you have n plus 2 the whole square into 3 raised to n plus 2, okay. Then you will have minus 6 into 3 raised to n plus 1 into n plus 1 square is there, okay. Then you will have plus b into 3 raised to b is already there, 3 raised to n into n square. Now all these things will be equal to 3 into 2 raised to n plus 7 into 3 raised to n. So you simplify this, what will you get? Okay, so you simplify this. So try to simplify this, what will you get then? Okay, so in order to solve this, we'll compare the coefficients of 2 raised to n and 3 raised to n on both sides. So we'll first try to see the coefficients of 2 raised to n. What are the coefficients of 2 raised to n in this problem? So it is actually in the first term there will be a is there, so 2 raised to n has 4 would be there because 2 raised to n plus 2 is there, minus 6a into 2 is there, okay. Then you have plus 9a. Now that coefficient will be equal to the coefficient of 2 raised to on the right hand side, which is nothing but 3. We can find the value of a from this. Similar to find b, you compare the coefficients of 3 raised to n. What are the coefficients of 3 raised to n? It is b into so in the right hand side it is 7 b into it is actually n plus 2 the whole square into 3 square minus 6 into then 3 raised to, so 3 into n plus square, okay. Then you have plus n square, okay. So plus n square into b there, here also will have b. Now that is equal to 7. So you have to solve both these equations to find the value of a and b. So what will be the value of a here? So what is it? It will be 4a minus 12a plus 9a, 4a minus 12a minus 8a plus 9a. It is actually a value of a is actually 3, and to find this you have to expand this. So what is it? So it is actually 9 into b into n plus 2 square, right? So it is 9 into b into n square plus 4n plus 4 minus 18 into b into n square plus 2n plus 1. Then you have plus n square into b is equal to 7. From this you try to find the value of b. So what is it? So we'll have how many b square n squares are there? 9n square minus 8, so minus 9n square minus 8n square b is there, okay. Then you have plus 4, how many n's are there? Here there is 36n is there, then minus 36n is there, so it will get cancelled out, and then you have 9b into 4 is there, so it is actually 36b minus 18, so it is actually 36b minus 18b, so it is actually plus 18b, okay, is equal to 7. Okay, so the value of b is nothing but 7 divided by 18 minus n square into 8. So this is how you find the value of a and b. Now substitute the values in the given equation, you will get the general solution. Okay, so I hope you understand these problems also now. Okay, so we will do one more problem. So consider this problem: an plus 2 minus 4an plus 1 3 plus 3an is equal to 2 minus 200. So the solution will be of the form an is equal to an h plus a and p. Okay, so an h is the solution of the homogeneous equation, which is actually an plus 2 minus 4an plus 1 plus 3a raised to n is equal to 0. So the corresponding characteristic equation will be r square minus 4r plus 3 is equal to 0. The solution of this is actually r is equal to 3 comma 1. So the solution will have the form an is equal to c1 3 raised to n plus c2 1 raised to n, which is nothing but c2. Okay, now the right hand side is actually you have a and p you need to find. So the right hand is a constant. You can, so your solution would be a constant only. So but you can't take it as a constant, because you can see that in the homogeneous solution there is a constant already there, so there's a possibility that these constants will be combined. So in order to prevent the combination of these constants, we'll take the particular solution to be n into a. Okay, so because already there is a constant in the homogeneous solution, so that constant and this constant will be combined together. So to prevent that, we'll put an n there. Okay, so we'll assume the solution to be n into a. Now we'll find the value of n here, n here. So when you substitute in this given equation, it will be n plus 2 into a minus 4 n plus 1 into a plus 3 into n into a is equal to minus 200. Okay, so from this you can find the value of a, which is nothing but, so it is actually you will have a into n plus 3 into n minus 4 into n a. Okay, a into so n plus 3n minus 4n a, so this will get cancelled out, and you have plus 2a minus 4a, 2a minus 4a. Okay, so this is equal to minus 200, so we have minus 2a is equal to minus 200, so your a would be equal to 100. Okay, so the solution is nothing but 100n. That's the particular solution. So the entire solution would be an is equal to c1 3 raised to n plus c2 plus 100n. In order to find c1 and c2, they have given conditions. A naught is 3000 and a1 is 3300. So if you substitute a, when n is equal to 0, you will get a naught, which is nothing but c1 plus c2. Okay, this will be 0. So similarly, that is actually equal to 3000, and now a1 is 3300. So when you substitute n is equal to 1, you will have c1 into 3 plus c2 plus 100 is equal to 3300. From that you will have c1 3 plus c2 is equal to 3200. So you will have 3 c1 plus c2 is equal to 3003 will be equal to 3200. So if you subtract them, you will have 2 c1 is equal, your c1 is equal to 100. So your c1 will be equal to 100, then your c2 would be equal to 2000. I think it is actually 2900. So that is c1 and c2. The solution would be 100 into 3 raised to 9 plus 2900 plus 100. Okay, so that is it. So now we'll get to the final solution. So we'll just try a small problem here. So we'll try to write down the form of the problem here. So if your homogeneous non-homogeneous solution is this, the equation is this, your corresponding homogeneous equation, your corresponding characteristic equation will be r square minus 10n plus 21 is equal to 0. That is actually r would be equal to 7 comma 3. Okay, so if your right side is fn is 5, your particular solution format will be simply a naught. Okay, it is not there. Now if your right hand side is 3n square minus 2, this is second degree polynomial. So your right hand side would be again a general second degree polynomial, which is nothing but a3n square, second degree, so a2n square plus a1n, okay, plus a naught is equal a, so a naught, this is the form of your right hand side. So it is written here a3n square plus a2n plus a1, whatever may be. So that is it. And similarly, if your right hand is 7 into 11 raised to n, okay, so this 11 raised to n is not there in the solution, so the answer will be of some constant into 11 raised to n, your particular solution. And if it is of the form 31 into r raised to n, where r is not equal to 3 comma c, then anyway the whole solution will be of the form a into r raised to n. Okay, now if your right hand side is of the form 6 into 3 raised to n, okay, now you can't assume the particular solution to be a into r raised to n, 3 raised to n, because already 3 raised to n is there in the homogeneous part, so we'll supply an n to prevent it from combining. Okay, so similarly, if it is 2 into 3 raised to n minus 8 into 9 raised to n also, you have to be careful here. So that is also, it will be of the form a n into 3 raised to n, some a constant 3 raised to n plus some constant into some b into 9 raised to n. So these are the different forms of non-homogeneous recurrence relations. Only these types will be there. So I hope you understand at last. If you have any doubts, you can contact me. Okay, thank you all.